Here is a question on general organic chemistry. Read the question carefully and think about the answer. Let us solve it step by step. Let us first understand the key concept here. When a dianion reacts with only one equivalent of acid, H+, protonation occurs at the more basic, less stable anion site, leaving the more stable, more stabilized anion intact. Moving on to the next step. Identify the two anionic sites in the dianion. The dianion is CH2 is equal to C, OCH is equal to C, OCH3. It has two oxyanion, O sites. Site 1, left O on the terminal vinylic carbon adjacent to CH2 is equal to, this is an enolate where the negative charge is on oxygen of a vinyl system CH2 is equal to C, O dash. Site 2, right O on the internal carbon adjacent to CH3, this is an enolate where the negative charge is on oxygen of a system C, OCH3, which upon protonation at carbon gives a ketone, or protonation at oxygen gives an enol. Moving on to the next step. Assess relative stability of the two anions. The key question is which anion is more stable, and thus should remain unprotonated after addition of one equivalent of H+. The right side anion, COCH3 with conjugation through the double bond, corresponds to a resonance-stabilized enolate that is part of a conjugated system, CH3C is equal to O, CH is equal to an alpha-beta unsaturated ketone enolate, i.e., a cross-conjugated or extended enolate. This anion is stabilized by conjugation with the adjacent C is equal to C and inductive effects. The left side anion, CH2 is equal to C, O dash, is a simple vinyl alkoxide enolate with less extended conjugation. Alternatively, considering that the right anion, enolate of a methyl ketone, COCH3, when protonated gives a stable conjugated enone, methyl vinyl ketone type, while the left anion when protonated gives a less stable species. Product stability argument, the remaining monoanion after protonation should be the more stable one. The right side enolate, COCH3, is stabilized because it is an enolate of a ketone in a conjugated environment. If the left anion is protonated, we get CH3C is equal to O, CH is equal to C, OCH3, which is answer D, an enolate stabilized by conjugation with the adjacent carbonyl, forming an extended conjugated system, ketone CH is equal to C, OCH3, analogous to a stabilized beta-keto enolate. And for the final step, protonation of the terminal, left CH2 is equal to C, O site converts it to CH3C is equal to O, a methyl ketone, giving the product CH3C is equal to O, CH is equal to C, OCH3. This remaining monoanion in D is highly stabilized because it is a vinylogous or conjugated enolate. The O is conjugated through C is equal to C to the adjacent ketone carbonyl, creating an extended delocalized system. This cross-conjugated extended enolate is more stable than the simple vinyl alkoxide on the left side. Therefore, protonation preferentially occurs at the less stable, left anion, leaving the more stable, right, conjugated anion intact. A protonates the right O, leaving the left O intact. The left vinyl alkoxide is less stable, so this is not preferred. B protonates the left O, but gives an enol, or, rather than tautomerizing to ketone, under acidic conditions the enol would tautomerize, but the structure shown retains O. This is less stable than the keto form shown in D. C involves loss of conjugation, saturated bridge CH2, which would require more than simple protonation. E protonates incorrectly and gives a less stable arrangement. Therefore, the correct answer is D. Therefore, the correct answer is option D.